Hello everyone, once again I welcome you all to MSB lecture series on interpretive spectroscopy, and today let me discuss again on 31P NMR spectroscopy. In my previous lecture I gave you very good examples of identifying different isomers of square planar complex and also a square pyramidal complex, and also how to distinguish if the coordination number is 5 for a D8 system. Two possibilities are there. In having an appropriate geometry, that is square pyramidal geometry and trigonal bipyramidal geometry, and how these geometrical changes can happen with temperature. We saw in case of rhodium complex having tetrakis trimethyl phosphine methyl composition in its coordination sphere. So let me continue with more interesting examples in this lecture. So now I have given another interesting molecule here. Let us try to analyze the spectra given. This spectrum is of 195 platinum NMR. In this spectrum, if you see, we have two triplets of equal intensity. Then if you look into the structure here, we have platinum. Platinum is directly attached to N15. That means here enriched molecule with N15, and we have another molecule here, isocyanate, where we have carbon to nitrogen triple bond is there, and we have CH2s are there, and it seems hydrogen is not interfering in this NMR, 195 platinum NMR. So let us try to analyze, and first thing we should look into is this is enriched with 15, and 15N we know that I equals half. If it is interacting with platinum which is one bond apart, it should split the platinum signal into a doublet. And this should be 1J platinum 15N coupling. This will split into a doublet. Now we have each line is split into triplet of equal intensity, and here if triplet of equal intensity means we should think of nuclear spin value something else. And of course the in close vicinity we have 13C carbon here. Carbon doesn't split something like this here, because 13C has I equals half, and also its abundance is only 1%. There is a possibility of seeing satellites. But on the other hand, here we have 14N, and 14N we know that for 14N I equals 1. Now if it is splitting this one, we can use 2Ni plus 1 rule. 2, only one 14 nitrogen is there, and then its spin is 1 plus 1, so it will be 3 peaks. We have 3 peaks, and when I equals 1 and triplet is there, intensities are 1:1:1. So in this case it should split something like this. Unlike the splitting with nucleus with I equals half, where intensity will be 1:2:1, here it is 1:1:1, 1:1:1, and then if you assume this is 2J, this is 2J platinum N coupling, then it should appear something like this. We can correlate this one. This is 1J PT N15, and then if you take any of this separation, this is 2J PT 14N. So this is how, although it appears complicated, when you understand it becomes very easy. So this is 195 platinum NMR. This involves both 1J platinum 15N coupling as well as 2 bonds platinum 14N coupling. Normally we don't see 14N coupling, and in case if we get something like this, interpretation would be rather easy. So this is a typical 195 platinum NMR spectrum, and again when we look into 195 platinum, here it's very similar to carrying out 13C NMR measurement. Now I have given set of chemical shifts or spectra here, and then write the appropriate structures and match the corresponding 31P NMR spectrum for the following inorganic cages and explain. So that means 4 spectra are given, and I would be providing 4 molecules here, 4 molecules. Now we have to interpret and we have to identify which molecule has which spectrum here. Then if you look into P4, it is a tetrahedral molecule with P4 having each one having 3 bonds connected to each other. And now this is all the phosphorus atoms are identical, they are chemical and magnetic equivalent. As a result, one should expect a single resonance in its 31p NMR spectrum. So here one of that one, it could be this one. If I say one here, it can be this one or it can be this one here. Come back to that one. And now let's look into this molecule, and when we react P4 with excess of oxygen, and we can get P4O10. In the same way, if we react white phosphorus with sulfur, excess of sulfur, we can get the analogous sulfide compound, that is P4S10. And here all phosphorus atoms are pentavalent and tetracoordinated, having 1 phosphorus to sulfur double bond and 3 phosphorus to sulfur single bonds. As a result, all of them are chemically and magnetically equivalent, and molecule is very symmetric. As a result, we also expect for this one to show one peak here. So it could be this one or this one. And next, let's look into this molecule here. In this molecule, 2 phosphorus are in pentavalent state and 2 phosphorus are trivalent state. That means we have 2 different type of phosphorus atoms are there, we have here. And then these 2 are identical and these 2 are identical. So these 2 phosphorus are equidistant from trivalent phosphorus here, trivalent phosphorus. That means these 2 phosphorus can be coupled with trivalent phosphorus to give a triplet, and similarly pentavalent phosphorus also can couple with 2 trivalent phosphorus to give a triplet. That means the spectrum should have 2 triplets, and yes, this is 2 triplets, and this can be corresponding to this molecule here. Now if you look into 4th molecule here, in case of 4th molecule, one of the 4 phosphorus atoms has 3 PS bonds. So others, they keep PP bonds intact. Just by looking into the molecule, you should be able to tell that we have 2 different type of phosphorus atoms in a ratio 1:3, and this is one type. If I say this is A and these are all B, or if I say A, this can be X. I think it is appropriate to use letters from farthest, because one is very different from the rest of 3. So if I put A here, there should be X here. That means we are talking about AX3 spin system. In AX3 spin system, A will be coupled with 3X to give a quadrate. Delta A, if you look into it, it would be something like this quadrate, and if we look into delta X, so this will be a doublet. So these 3 are identical, they split with A to give a doublet, and then A will be split by 3X to give a quadrate. So we have here, okay, so this is for 4. Okay, so that means basically when we take white phosphorus and react with excess of sulfur, and it is likely that if we abruptly stop this reaction, it is likely that we can get all these products along with unreacted white phosphorus also. In that case, without any problem, we should be able to distinguish. Then how to distinguish between this one and this one? For that one, we have to take the spectrum of pure white phosphorus, then we should be able to identify. Or we do excess of reaction for this isolated molecule you take, and then we should be able to distinguish between this one and this one. So this is how, when we get more than one type of product in a reaction mixture, and if we have phosphorus in it, it's very easy to distinguish these and identify the corresponding products. So here, that's the explanation I have given here. This one you can call it as A2 X2 spin system, and this is AX3 spin system. Now let us look into the NMR spectrum of PF5, both 31p NMR and 19f NMR. PF5, we all know that it is highly fluxional molecule and it is trigonal bipyramidal, and because of fluxionality, what happens, we may not be able to distinguish axial fluorine with equatorial ones. So at room temperature, if you record 31p NMR, So all are identical. As I said, we cannot distinguish between equatorial and axial ones. As a result, all the 5 would be coupled with phosphorus to give a 5 are their sextet. It should give so 6 lines will be there, and it should appear something like this. Okay, this is 31P NMR spectrum. Now, if you look into fluorine NMR, again you cannot distinguish between axial and equatorial. As a result, you will see a single resonance for all the fluorine atoms, but that is coupled with phosphorus, so it appears as a simple doublet, something like this. Okay. But if the molecule is static, what would happen? Okay, next question is, if the molecule is static, then let us look into 19F spectrum. If the molecule is static, then this is axial and this is equatorial. So let us say then there are 2 possibilities. First, it can interact with the axial ones, or it can also interact with equatorial ones. That means unless we know the magnitude of the coupling constant of phosphorus with equatorial fluorine and axial fluorine, we may not be able to tell it. But on the other hand, if the molecule is frozen, say let us say minus 80 degrees centigrade, when we take it, we assume that all dynamic process comes to an halt and it is static, so that there is no Berry pseudo rotation to exchange axial ones with equatorial one. In that case, if we record the spectrum, we should be able to tell simply by looking into the spectral pattern whether the fluorine to phosphorus axial is larger in magnitude or phosphorus to equatorial fluorine coupling is maximum. So let us look into both the cases here. First, let us assume 1J P F axial is greater than 1J P F equatorial. So now first what would happen is the phosphorus signal will be split into a triplet here, and then each line will be split into a quadret. So something like this. That means it is basically a triplet of quadrets we will see. A triplet of quadrets we will see. On the other hand, if we see PF equatorial is greater than 1J PF axial, first they split this into a quadret, and then each one will be split into a triplet here because of 2 axial ones. And this one is J P F E, and now each one will be split into triplet. Okay, so this coupling will be here axial. In this case, it appears like something like this. So now by simply looking into the spectrum, we should be able to tell whether magnitude of phosphorus to fluorine axial one is larger or phosphorus to fluorine equatorial is larger. So these two. This one will be something like this. This is a triplet. Something like this it shows. Of course, here it is 1:3:3:1 is maintained, and overall it is 1:2:1 is maintained. So this is how we can sketch NMR spectrum of looking into the coupling tree. We call this as coupling tree. Now I have 3 more examples here. Sketch the 19F NMR spectrum of P5 that I have already done. Sketch the respective NMR spectrum for the following compound showing all reasonable couplings here. So let us take one at a time. And again, if you look into first molecule here, we have a square planar complex, And in this one again we have two isotopes are there, 196 platinum with I equals 0, that is 66%, and then 195 platinum I equals half with 34% abundance. And now we have one phosphorus that is directly connected to phosphorus, and then we have phosphine imine. We have another phosphorus, this pentavalent, and this, if you say this one A, this is X, and also this is M. So we are talking about AMX spin system. AMX spin system differs little bit in the sense M is not 100% abundant, whereas in this case we can see very identical, but instead of phenyl groups on phosphorus we have fluorine are there and another NMR active nuclei, and here we have P double bond S. That means basically we can talk, this is one type, this is another type, and this is another type, and this is another type. So that means we have, in case of 31P NMR, we can anticipate two signals and each signal will be split in a different way. And then if you just look into this case, it is very interesting, and if you just look into 14N NMR, let us say 14N NMR, what would happen is hydrogen is also one bond apart and phosphorus is also one bond apart. In this case we have to see different situation here. So one is nitrogen to hydrogen coupling is larger than nitrogen to phosphorus coupling. On the other hand, nitrogen to phosphorus coupling is larger than nitrogen to hydrogen coupling, and the third one is both the couplings are identical. That means if somebody asks you to sketch the 14N NMR spectrum of this molecule without knowing the difference in the magnitude of these couplings, we should be able to sketch all three possible ones, and after plotting or recording actual NMR spectrum we can compare and we can conclude what actually it is. So let us take one at a time. Now let us look into 195 platinum NMR spectrum of this molecule here. First, this platinum is coupled with phosphorus, this one bond apart, to give a doublet, and each line in the doublet will be further split into another doublet because of 2J platinum to phosphorus coupling here. So that is shown here, and this corresponds to 2J platinum phosphorus coupling, and this corresponds to 1J platinum phosphorus coupling. So it shows a doublet of doublet. Now I would come back to phosphorus NMR. Now let us look into this molecule here. Here a PP bonded compound with one of the phosphorus is oxidized with selenium. So selenium again, 77 selenium is about 0.6%, I think 7.6% natural abundance is there, and I equals half, rest is 76 selenium which is NMR inactive. But when you are looking to 77 selenium NMR, first this will be coupled with doubly bound, it's a one bond phosphorus, and this coupling comes anywhere between 780 to 1200 hertz. First it splits by this one, and then we have two bond coupling also that will split each line into another doublet, and this coupling magnitude is much lower. It can be anywhere between up to 50 hertz or 100 hertz. So you can see it also appears as a doublet of doublet. And then if you look into platinum compound here, phosphorus NMR, let us look into the phosphorus NMR here, 31P NMR. So in 31P NMR, if you just look into 66% NMR inactive molecules, platinum inactive I equals 0 molecules, what we get is we get a doublet here and a doublet here. This is simply 2J PP coupling, one 2J PP coupling, and this is 2J PP coupling. So let us say this is PO and then this is PN, something like this we can denote. And now what happens, this accounts for 66% of molecules. Out of 100 molecules, 66 have 196. This corresponds to 196 platinum bond. But how about 195 platinum bond? They will be split further. So something like this, a doublet, and then doublet, something like this. Now this coupling and this coupling. So this is for the PO, 1J PT PO coupling, and this is 1J PT PN coupling. So this can be anywhere between 2500 to it can go to as high as 7000 hertz. So we should be able to again draw 31P NMR or sketch 31P NMR spectrum for this molecule here. And if we sketch phosphorus NMR here, for this one again both are different AX spin system. We can get something like this. And now this selenium is also there. So what happens, the one that is, say if it is selenium bound and this is with lone pair, this one will be split and it will be splitting something like this, and then we will be having satellites here, and then this coupling what we call it as 1J PSC coupling here. And whereas this one, it is less likely to show, even if it shows the coupling magnitude is very small. Let us say if it is there, it will be something like this, it will be there, and then in this case it is 2J PSC coupling. So once we know the relationship and what is the natural abundance, we should be able to catch appropriate NMR spectrum no matter which nuclei we are talking about. So let me stop here and come up with a few more interesting molecules in my next lecture. So I showed you here a rhodium compound. Let me discuss NMR spectrum of that rhodium compound in my next lecture. Until then, have an excellent time. Thank you.